Hello. How is everyone doing? Yeah, it's post-lunch. I understand that. So welcome to the Container Infrastructure Keynote. This is a new format we're experimenting with for this OpenStack Summit with specific keynote segment for specific focus areas. So we've been having CI/CD keynotes this morning as part of OpenDev. We'll be having Edge infrastructure keynote tomorrow morning in this room. And this is the Container Infrastructure Keynote. Containers are obviously a popular way to consume infrastructure those days. But if you look at production deployments end-to-end from bare metal up to container orchestration platforms, there are a number of unanswered questions, especially if you look at the problem from a security perspective or multitenancy. And so to fill those integration gaps, we're encouraging open discussions on this topic during this summit, especially trying to have discussions about security in the open. Security resonates with me personally a lot because I started my open source journey 16 years ago by contributing to the Gentoo Linux security team. And that's why I'm excited with our first speaker, who comes from a company that knows a thing or two about container and security. Please give a warm welcome to Maja Kaczorowski.
Thanks, Terry. Oh, my computer's been locked. That's how secure we are. All right. So my name is Maya. I'm a product manager in security at Google, and I focus specifically on containers. And I'll be talking a lot about isolation today and how isolation works in Kubernetes, because that's what I know pretty well. So what does that mean? What kinds of threats are there to containers? Well, first is the threats that you have to container peripherals, like credential compromise and privilege escalation. This is about how you get the Kubernetes API to do something you might not want it to do. Second category is what ends up running in your infrastructure. You might be pulling images from public repositories or have dependencies on unsupported open source code. If a new O-Day vulnerability is dropped, like today, how do you figure out if you're affected, and how do you quickly patch yourself? And then there are things that we hear people get really, really scared about, which is things like, can you DOS me? Can you DOS my event pipeline? Can you use my container for cryptocurrency mining? And what's usually lumped in the last category as well is container escapes, right? But unlike all the other threats that we're talking about here, container escape is fundamentally different in that it affects containers only. Everything else we talked about affects any system that you're running in, no matter which infrastructure you're on. So I want to point out, though, that container escapes are theoretically possible and doable in test environments, but we haven't seen them in the wild yet. At least I haven't. So if you've seen something interesting in the wild, please come tell me afterwards. What does this mean, and what kind of controls are you going to want to have in place when securing your containers? We have three main pillars following the threats that we had before. How do you develop your applications? How do you manage your images for security? And how do you protect your containers while they're running? So the first category, infrastructure security, is about ensuring that your developers have the tools that they need to build containerized services securely. This includes identity and access management, networking, secret management, and logging, right? Nothing new, nothing that we haven't seen outside of containers. The software supply chain is the middle category here. It ensures about making sure that you know exactly what's deployed in your environment and that it belongs there. This is about securing the host image, the container image, and the code itself that you're running. Lastly, runtime security is about ensuring that your security response team can detect and respond to security threats to containers running in your production infrastructure. And this is extra interesting and cool and where some of these threats come into play. And so what kind of threats do we really have? Well, we have threats from the outside, and we have threats from the inside. From the outside, you might be worried about preventing an attacker from stealing data or credentials or compute time, right? That's what cryptocurrency mining is. You might also be worried about preventing an attacker from altering or disrupting a service. Somebody can DOS your service, for example. Most of the threats that you're thinking about when you think about container security is in this kind of outside category of threats. From the inside, though, you're worried about a different category of threats. You're worried about a process escaping and affecting another process, for example, using shared resources. This is exactly what you're talking about when we talk about container escape. And this is a super interesting concern. So why are we worried about threats from the inside? And is this a reasonable concern? Let's talk about what's fundamentally different between a VM and a container that affects security. For VMs, you have a host OS running on top of hardware, and then you're running a hypervisor on top, which then isolates each individual VM. Each application, its own virtual machine, has its own guest OS, binaries, and libraries. For containers, you have a smaller host OS, and on top of that, a container runtime. The binaries and libraries are separated for each individual app and shared by the applications that require them. So what's different from a security point of view? Well, one is that smaller host OS, right? It's a smaller surface of attack than what you had on a VM, which is a good thing. At the same time, a VM uses a hypervisor, but we don't have that on a VM. On a container. And a hypervisor is something that the industry really trusts and understands, or rather, people who are smarter than me understand how hypervisors work. For containers, the container runtime doesn't necessarily provide the same level of isolation. So I've skipped over kind of all the other pieces because, truthfully, from a security point of view, they don't really matter. It's not all that different. You can take the same constructs that you already know and apply them to containers. So if you want a firewall, sure, have a firewall. You want an IDS IPS, like no problem. You want secret management, like you got it. A lot of the constructs are the same, except for some of the key things we're pointing out here. All right, so with containers, I have a smaller surface of attack. That's a good thing. But I also don't have a hypervisor. So how am I supposed to do isolation? And this is when you're thinking, like, this is so silly. Containers have contain right in the name. They contain. No, they don't. We really, really wish that they did, but they don't. Containers aren't meant for containing. If you remember one thing from this presentation, it's this key message. While containers have great benefits to your development pipeline and provide some resource separation, they weren't really meant to provide what I'll call a strong security boundary. Containers contain like a cup of water, not like a thermos. So you can carry a cup of water back to your desk, a tea, hot tea or whatever, and it'll spill a little bit and you're going to burn yourself. And it's going to suck. Containers are good at containing dependencies. They're not good at containing code from a security point of view. OK, so now that we know that containers don't contain, like, do we even care? Why do we need isolation? The fact is, you might want to be running untrusted code in your environment. So untrusted code, it lives on a spectrum, right? On one end of the spectrum, you have code that is known to be bad. Malware that you're analyzing, you're doing reverse engineering for in your infrastructure. And the other end, you just have code that you just haven't tested yourself. It might be some open source component that you haven't audited. You might also have a project that historically had known security vulnerabilities, and you're just a little bit worried about running in your infrastructure. In each of these cases, though, the point is that you don't want the code to affect the security of your own workloads. Beyond untrusted code, there are other reasons you might want isolation. It's just a best practice to follow in terms of reducing the surface of attack of your environment. Or you might be wanting to offer a multi-tenant environment for your customers and make sure that they're separated. Or you might be in a multi-tenant environment and want to make sure you have sufficient isolation from everybody else running there. Applications that run in traditional Linux containers really access resources in the same way that applications which don't run in containers access system resources in the same way that applications that don't run in containers, by making system calls to the host kernel directly. And this kernel runs in a privileged mode, which allows it to interact with the necessary hardware and return the results, right? With traditional containers, the kernel imposes some limits on the resources that the application can access. And this is done through things like Linux C groups and namespaces. But not all resources can be controlled via these mechanisms. And even with those things in place, the kernel still exposes a large surface area that malicious applications can attack directly. So there is a need for stronger, better isolation. Let's talk about a slightly different concept, which is not only is the level of the code, is the level of trust of your code relative, but the trust that you require is relative. So you might not have the same requirements for all the code that you're going to run. The more sensitive the data you process, the more you need to be able to trust the software that accesses it. You wouldn't treat code that doesn't access user data the same way that code that does, or that is in the serving path of your application, or has root cluster access. In a perfect world, from a security point of view, you would access your most critical data only with code that you wrote, that you audited, that you ran some automated security checks on, like fuzzing, and then you would verify that all those checks passed before you deployed that code. Of course, the actual requirements that you have might change depending on the environment, right? So you might be able to trust an open source component if it's running in a test environment for a game app that you're developing in your spare time, but not trust it if it's running in a critical hospital system accessing patient data. So a trust boundary is the point at which your code changes the level of trust, and hence its security requirements. And a security boundary is how you enforce those trust boundaries. A security boundary is a set of controls managed together across all surfaces to prevent a process from one trust level to elevate its trust level and access more trusted processes or access user data that it shouldn't be accessing. At Google, we aim to protect all trust boundaries with at least 2 security boundaries, so that they need to fail independently in order to cross the trust boundary. Traditionally, you might have put untrusted code in its own virtual machine, relying on the hypervisor, like we were talking about earlier, to prevent processes from escaping or affecting another process. A hypervisor is a fairly strong security boundary in that we don't expect code to be able to escape from one VM, go through the kernel, or otherwise go through the hypervisor and talk to the other VM. At Google, we use the KVM hypervisor and put a significant amount of effort into ensuring its security. But what about containers? Well, a container is one security boundary, although it's not a super strong one. It's because compared to a hypervisor, a native OS container is larger, more complex, and has more potential vulnerabilities. You can still use security features, though, like seccomp to help remediate this, but it's still just one boundary. It's not the desired 2 boundaries that we want. OK, so let's talk about isolation in Kubernetes and in containers, and like what you get at each level. So there are lots of different kinds of isolation we can talk about. We can talk about kernel security isolation, which is about the independence of talking to your kernel. Resource isolation, which is how you access shared resources like storage. Service account isolation, which is the identity of the thing that you're running and how it talks to other services, how it identifies itself elsewhere. Control plane isolation, which is talking to, like, for example, the Kubernetes API master and what's restricted. Workload metadata isolation, which is information about your workloads, including the workload name, the workload size. Data isolation, which is the actual data of your workloads. And a network isolation, which is how traffic flows in your environment. That's a lot. OK. Now, let's talk about what actually happens at the levels. Kubernetes has several nested layers, starting with a container, which is not a Kubernetes construct. It's a Linux construct, and building on top of that to give you different isolation, right? The higher up you go, the more isolation you get. So starting from the smallest unit and moving outwards, we have a container. A container is not specific to Kubernetes and provides some basic management of resources. It just doesn't isolate identity or network. And it can still suffer from the noisy neighbor problem of somebody else running on the same node for resources not isolated by cgroups. It provides some security isolation, but only that single layer compared to that double layer that we're going for. Next up, we have a pod. A pod is a collection of containers and isolates a few more resources than a container does. At the moment, a pod doesn't have a strong notion of identity, although there are a couple of proposals in the Kubernetes community to provide that in the future. A pod still suffers from the noisy neighbor problem. It gives us more resource isolation and also gives us a bit of network isolation. In Kubernetes, you can use the Kubernetes network policy to provide some microsegmentation. It lets you limit which pods talk to which other pods. It's worth remembering, though, that the network policy is open by default, so please go set that if you haven't set one. Next up, a namespace. A namespace is a collection of pods, and it's the fundamental unit of authorization in Kubernetes. Namespaces provide some control in terms of authorization versus namespace level RBAC, but don't attempt to control resource quota, network, or policies. They allow you to easily allocate resources to certain processes, and they're meant to help you manage how you use your resources, but not necessarily prevent a malicious process from escaping. Since it's the unit of authorization, it gives us the Kubernetes service account isolation, and also gives us a little bit of control plane isolation in that those requests have to be authenticated, so it is dependent on that identity. The node. A node is a machine, either a physical or virtual machine. It includes a collection of pods and has a superset of privileges of those pods. It leverages a hypervisor or hardware for isolation, including for resources. And it's good at that, right? Node has isolation that we're familiar with. It has a hypervisor. It gives us the strongest resource isolation, and we can use traditional networking to isolate the node, including things like firewalls. A cluster is a collection of nodes and a control plane, and this is the management layer for your containers. They offer stronger network isolation with per cluster DNS and provides isolation of metadata in that the cluster won't be able to see another workload's resources name and use, for example. So if you're sharing a cluster with the cookie monster, don't have top secret cookie recipe in there. He'll be able to see that you have that workload. And then the last layer is usually cloud provider dependent. So at Google, we have this thing called projects on GCP, and it's the final layer of isolation. It provides things like project-level IAM and org policies. And this is also when you can do kind of the most network isolation with things like VPCs. So I often get asked, like, what do I rely on? Like, if I want to run a multi-tenant workload, what do I actually need to do? Does each person need their own cluster? Do they each need their own node? Like, what am I trying to do? It's a terrible answer, but it depends. The choice that you have for isolation depends on what your workload really needs, right? Like, what you need is what your workload needs. So there's no one-size-fits-all answer. OK, so say you've decided what layer of isolation you're going to go with. Let's talk about sandboxes. You might typically think of sandboxes as a testing environment, something that you use to isolate like tests from prod, and you do some software development in there, you do some malware analysis in there, et cetera. And that's pretty close. We just mean that a sandbox is an isolated environment that can't affect those around it. But you can be running it in prod, too. What's exciting for containers is that containers are all about running different environments together, right? They're about better bin packing what's on your node. So we run sandbox containers. We can start to run things that we wouldn't have been able to otherwise run together on the same node, different environments on the same node that we might have been hesitant to pack together before. Sandboxes really allow containers to reach their full potential in terms of maximizing your resource use. So you've decided to run a multi-tenant environment, and you want to be able to have stronger isolation. Again, like I said, a container might not be good enough in the sense that it's one layer, right? We need a separate layer. We need like a second kernel, for example, a separate kernel. So practically, how do you run a sandbox? How do you run a containerized sandbox? Well, there are great efforts in the Kubernetes community right now to extend the isolation properties of sandboxes to pods. Note I said pods, not containers. And the sandbox pod API is currently being formalized, but there's still some experimental support already available. The core idea of a sandbox pod is that you can run multiple containers in a pod on a shared node and isolate each pod with having its own kernel that it can use to perform operations. So what are my options? I'm sure some of you are familiar with Kata containers. That's what a lot of you are here for that, I'm sure. First off, so Kata containers was announced in December at KubeCon as a new project combining Intel Clear containers and Hyper-Run V. The idea here is to build a really simple, lightweight virtual machine. Hey, remember, those are good at containing, and using that to contain my workload. The sandbox has a stripped-down guest kernel to limit possible actions. And in this model, each pod is hypervisor isolated, as secure as a VM, and aims to be as fast as a container. It's plug and play with a Kubernetes container runtime interface, a CRI. And I'm not going to dig too deep, because I think you're about to hear a lot more about Kata containers. So ultimately, Kata is aiming to eliminate the need to nest containers inside fully fledged virtual machines, giving each container its own machine with its own kernel and virtualized devices that it can use. Another option is something called gvisor. gvisor is Google's internal sandboxing technology that was just open sourced a few weeks ago at KubeCon in Copenhagen. Like Kata containers, gvisor is a new kind of sandbox, helps provide secure isolation for containers while being more lightweight than a VM. It also integrates with Kubernetes' CRI, making it simple and easy to run sandbox containers. The main differences are around how gvisor runs. The core of gvisor is a kernel that runs as a normal, unprivileged process that supports most Linux system calls. It's not meant to be able to run every single application. Think of gvisor more as like as a most-purpose sandbox, not an all-purpose sandbox. So we're done, right? We have sandboxes, we have lots of options, we can solve everything. So what's left? Just because you're isolating your workload doesn't mean you're done. You still have a ton of risks. From storage point of view, storage is, if you can pass through data, it's not a security boundary. Networking, remember, you have to still set a network policy, et cetera. And so what's the overall takeaway here that we have? Containers don't contain, remember that, let's not forget. Kubernetes is complex and subject to internal threats. And so if you're going to try to do something multi-tenant, requiring isolation, a bit untrusted in Kubernetes, first pick the right layer of isolation that you need, and then use sandboxes to mitigate risks. So I hope that was a useful crash course in isolation in Kubernetes. Thank you so much for having me.